Welcome back to Physics 151 Online. We're now going to launch into a discussion of a new subject, and that's called internal energy. We'll see that as we define internal energy and what that means for a system of particles, it's related to the specific heat that we've already talked about, and then with those definitions in place, we'll be able to introduce the first law of thermodynamics. So, a little bit of history first. In the early to mid-1800s, the modern theory of heat as a form of energy replaced an older theory, and that older theory regarded the thermal properties of a system as being contained in the amount of caloric that substance contained. Caloric was thought to be a property of a material, and it was an indestructible substance. So at the time, people thought that you could transfer a certain amount of caloric from one object to another in a similar way that fluids can be poured from one container to another. And although there are some similarities that this earlier theory has with the modern theory of heat flow and thermodynamics, also there were some misnomers. And in particular, people did not realize that this caloric, or what we now call heat, was a form of energy and was actually just a slightly different form of what was already known as mechanical energy. And so that was really the breakthrough that happened in the mid-1800s. James Joule, who we see a picture of right here, did some very clever experiments that showed that mechanical energy and heat were really just different forms of the same things. And this is the origin of the modern science of thermodynamics. So, a couple of definitions. We already know about mechanical energy. We've defined E as the sum of the kinetic and potential energies associated with the position and motion of an object, and to be more precise, we should say associated with the position and motion of the center of mass of the object. So if I take a baseball and throw it through the air, its center of mass is translating through the air, and so the entire object moves along with it. So mechanical energy just has to do with the kinetic and potential energies that object has by virtue of the position and motion of its center of mass. But that doesn't say anything at all about the constituents of that object. So inside the baseball, the different atoms and molecules that the baseball is made up of are basically just along for the ride when we're talking about mechanical energy. Internal energy, by contrast, adds up the kinetic and potential energies of all of the atoms, molecules, nuclei, whatever else is inside the nucleus of which an object is composed. So the atoms and molecules and nuclei all are translating with the object that's moving, but they each have their own kinetic and potential energies. And a simple way to think about this is to realize that atoms are basically acting like little masses that are connected to one another through chemical bonds, and you can think of a chemical bond as a spring. And so these atoms oscillate back and forth like a mass connected to a spring, and they have their own kinetic and potential energies. So when we now talk about the internal energy of an object or of a system, it's the kind of energy associated with the kinetic and potential energies of the component particles. Now, for an ideal gas, the situation is a little bit simpler because the molecules are dilute enough, as we've talked about before, that we can ignore the potential energy between those molecules. Even though when they get really close, they do attract one another and they do occasionally collide, we're going to ignore all of those things for a dilute system. And we can also ignore the kinetic and potential energies of the nuclei and the smaller particles that make up the gas molecules, because they don't change unless a nuclear reaction is taking place. So the protons and neutrons inside the nucleus do have kinetic and potential energies, but unless the nucleus breaks up and then forms a new nucleus, those protons and neutrons have the same energy all throughout the motion of an object that has those protons and neutrons inside. So we're just going to ignore the energies of those particles. So what we now can do is look back on our result for the translational kinetic energy of an ideal gas made up of capital N particles or little n number of moles, and realize that the internal energy, if we ignore the potential energies because they're basically negligible, the internal energy is just made up of the translational kinetic energy of the gas molecules. And we'll put a subscript on here because we'll find out later on that when we talk about more complicated gas molecules that are not just made up of a single atom, we have to change this equation a little bit. But for a system like helium, where the gas molecules are simply atoms, then the internal energy can be written in the form 3/2 nRT. And the 3 comes from the fact that we have 3 dimensions for those particles to move around in. Now, from our study of calorimetry, we remember that thermal energy, or the heat that's transferred to an object or to a system, can be written down as Q equals mc delta T, or the number of moles times the molar specific heat times delta T. All right, and there's a little bit of a qualification that we have to make here, and it has to do with how these experiments are done. When experimentally we measure the molar specific heat, we do it differently for liquids and solids than we do for gases. For a liquid or a solid, when we measure C, we do it under conditions of constant pressure, because in the laboratory we're working at an ambient pressure of about 1 atmosphere. And so we write the value that we determine experimentally under those conditions as C sub P, which means the molar specific heat at constant pressure. Now a gas is different, right? Because for a gas, it's usually trapped in some kind of a container that has a fixed volume. And so we measure, when we transfer a certain amount of heat to a gas and then measure its temperature rise, the value for the specific heat that we get is for the specific heat at a constant volume. And the C sub P and C sub V values, if we were to measure them for, let's say, a gas, if we measured the specific heat under conditions of constant pressure versus constant volume, we would get slightly different results. So, but usually with gases, those measurements are done at constant volumes. So let's assume that heat flows into a gas at a constant volume, and if that's the case, the gas cannot expand or be compressed. In other words, we can't do any work on the gas, and the gas can't do any work on its surroundings because the volume stays constant. So the heat that flows in, the thermal energy that comes in, all has to go into changing the internal energy of the gas molecules. And as a result, we can take our formula for Q, N, and I'm going to explicitly write it now as C sub V, the specific heat at constant volume. So N C sub V delta T for Q then has to just equal the change in the internal energy U. And we already know from our previous slide that for a monatomic system, that's 3/2 nR times delta T. So what we can do by just comparing these two equations is we can see that the internal energy for an ideal gas can be written as the number of moles times the specific heat at constant volume times the temperature, right? Because what we have here is a relationship involving the change in the internal energy and the change in the temperature. So that equality implies that we can write down the internal energy in this form. And then by matching up the C sub V with the 3/2 R, we see that for this ideal gas, for a monatomic ideal gas, C sub V is 3/2 times the gas constant. Now, what about other kinds of molecules? I mentioned them already, and there's a significant difference, because when heat flows into a gas that's made up of just monatomic molecules, single atom molecules, then all of that thermal energy goes into increasing the translational kinetic energy. But if you have a diatomic gas like oxygen, or a polyatomic ideal gas like methane, those can have not only translational energy, but they can also have rotational as well as vibrational energies. So when these kinds of gases absorb thermal energy, some of that thermal energy increases their translational kinetic energy, like it does for a monatomic gas, but as well, some of that heat is transferred into rotational or vibrational energy. And this means that the specific heat value for diatomic or more complicated polyatomic gases is different than it is for a monatomic system. And it turns out that we can write a general expression for the specific heat using a constant gamma that's specific to a particular kind of gas molecule. So the general way to write this down is C sub V is equal to R, the gas constant, over gamma minus 1. Now, what value does gamma have? Well, evidently, since we know for a monatomic ideal gas, C sub V is 3/2 times R, that means that the gamma for a monatomic gas must be 5/3, right? Because 5/3 minus 1 that would give 2/3. The reciprocal of 2/3 is 3/2. So that would give the right relationship, right? So that we see this familiar result, C sub V for a monatomic gas is 3/2 R. And that also means, as we wrote down on the previous slide, that the internal energy can be written as 3/2 nRT. Let's now compare for a diatomic system. We can do some experiments, and also we can understand, based on the idea of the rotational energies for a diatomic gas molecule, that this gamma factor must have the value of approximately 7/5 or 1.4 for a diatomic gas. So when you put that into the denominator, 7/5 minus 1 is 2/5, so we get 5/2 as the multiple of R for the specific heat of a diatomic gas molecule. And then the diatomic internal energy would be 5/2 nRT. So your textbook will have a table of values of gamma for different gases. Many of them, the monatomic and the diatomic gases, will have values that are very close to these ideal values. However, you may find examples in that table that differ slightly from these particular values here, because those gases may have slightly non-ideal behavior. So if you're provided with a gamma value in a homework problem, use this equation here to calculate the specific heat that would be appropriate for that value of gamma. All right, now finally we're ready to state the first law of thermodynamics, and this will be the starting point for the next part of the course, when we will go on to work problems involving expansions of gases or compressions of gases, and then be able to understand the operation of heat engines. So the internal energy of a system can only change through one of the following processes. Okay, either thermal energy can be absorbed by the system or released by it, and if that happens, then the internal energy will change. And then secondly, this is the process that we ignored a few minutes ago, there could be work done by the system or work done on the system, and that would involve either a compression or an expansion. So those are the only two ways that the internal energy, remember, internal energy is the sum of the kinetic and potential energies of all the particles that make up the system. The only way it can change is through one of these two processes. And if energy is conserved at the microscopic scale the same way that it's conserved at the macroscopic level, then any change in the internal energy of a system like a collection of gas molecules must be equal to Q minus W. And this definition assumes a certain kind of sign convention. It's important in thermodynamics to adopt a sign convention that then, if you follow it consistently, will give you reliable results. So think about this definition. Delta U, which is the change in the internal energy, would be positive if heat flows in, right? And so if Q is positive, then delta U is positive, and that corresponds to heat flowing in. So Q greater than 0 means heat flows into the system or heat is absorbed by the system, and conversely, if Q were negative, that means heat is released. So that's the sign convention for heat. Likewise, okay, think about a system of gas molecules. If that system does work on its environment, it has to do that at the expense of some of its internal energy, right? So the gas molecules, if they push on a piston and cause that piston to move, those gas molecules are doing work as the volume expands. So they do that at the same time as they lose internal energy. And so the energy balance here makes sense. That minus sign makes sense if positive W means that the system is doing work. That corresponds to an expansion. Negative W then would correspond to the system being compressed. And if a system is compressed, right, then W is negative, minus a negative would be a positive, and the internal energy would go up. So these are the sign conventions that we're going to use in all of our calculations when we look at a particular process and calculate the heat, the work done, and therefore the change in the internal energy. So more on this topic later. Hopefully this has been a useful introduction. I'll see you in class.